If you use a graphics tablet, you probably know that the technology behind the tablet and the pen is called EMR. That stands for Electromagnetic Resonance. In this video, I'm going to give you an overview of how this technology works. The EMR technology was invented by Wacom decades ago. Those initial EMR patents by Wacom have since expired, which is now why you see EMR technology adopted by manufacturers such as Huion and XP Pen. I got interested in this topic because, embarrassingly, I stepped on and broke one of my Wacom pens, and I was really surprised what I found inside. So I started doing some research, and I put that all together in this video. Now, this video is for people like me who use graphics tablets for creative applications. This isn't for electrical engineers or experts in electronics. So I am really simplifying a lot of things and leaving out a lot of details. If you think I've gotten something wrong or I need to add more detail, please leave a comment. We're going to start from an incandescent light bulb. And to make the light bulb shine, it needs power. So what you see in this diagram is on the left, there's the source of some power, which is a constant current that's always flowing in a certain direction. So this is DC power, direct current. Alternatively, we can use AC power. This means alternating current. This means that the current is always changing its magnitude and its direction. Now, how can we wirelessly power this light bulb without it being directly connected to the source of power? Well, we're going to split it apart into two circuits. One has the AC power and one has the light bulb. And how we transfer the power, on both those circuits, we're going to coil the wire in some loops. And what happens because of this is that as the AC current flows on the left, it creates a continuously changing magnetic field on the left coil. That magnetic field then induces a current on the right coil. A couple of points we should make about what's going on here. These coils are called inductors, and it's a very simple electric component. And they're called inductors because, of course, they induce a current. Now, how much an inductor can do its job is measured by something called its inductance. And we can control the amount of inductance by changing the number of coils. We could have one coil or many coils. We could increase the size of the coils. We could put something within the coil, like something called a ferrite rod. Another interesting point about an inductor, and it's not obvious from the diagram, is that an inductor stores energy in the magnetic field that it develops. In fact, if the current stops, the magnetic field will collapse, and it will release that stored energy as more current. So in a sense, an inductor you could think of as acting as a temporary battery. In the diagram, I show an equivalent number of coils on the left and the right. And there's no reason why this must be true. Depending on what we are trying to accomplish, we could have any number on the left or right. For example, we could have 1 on the left and 30 on the right if we wanted to. Picking the number of coils is an interesting topic, but not so important to understand this video, so I won't mention anything more about it. For now, let's just focus on the light bulb circuit, and this will become an EMR pen very soon. We're going to remove the light bulb and replace it with something called a capacitor. A capacitor is very simple. It's basically two plates of conductive material separated by something. That something can be air or ceramic or glass or paper. In this case, we'll just stick to air. Like an inductor, a capacitor can store and release energy. But whereas an inductor stores energy in the magnetic field, a capacitor stores energy in an electrical field. The degree to which a capacitor can store energy in the electrical field is called its capacitance, and it is controlled by the size of the plates, the distance between the plates, and what substance is between the two plates. When we have an inductor and a capacitor in a circuit like this, it's called an LC circuit. For the name LC circuit, the L refers to the inductor and the C refers to the capacitor. It's also called a resonance circuit, and the reason for that will be clear in a little bit. Now let's take a look at an LC circuit in action. Now what I've done is I've added a little bit of extra to the left just so it provides some power to the circuit. And there's a switch at the top, which I'll open, and then we'll see what happens to the LC circuit when there's no more power being delivered to it. So now I'm going to open the switch. Now look what happens. There's current moving back and forth, and what's happening is this current is sort of being absorbed by the capacitor on one side, being released back into the inductor. And the inductor, of course, it's growing its magnetic field, and that magnetic field is collapsing and sending more current back down the other side to the other plate to the capacitor, and then that bounces back and goes back and forth really fast. This is what is resonating. Now, the resonance happens at a certain frequency, that is the resonant frequency, that is controlled by the capacitance of the capacitor and the inductance of the inductor. And if we modify them slightly, there will be a very different resonant frequency. Now, as the circuit is resonating, the inductor will be at that same frequency, building up and collapsing its magnetic field. And if you were to measure the magnetic field around the inductor, you'd see it go up and down and change directions like this in this wave pattern. Now, of course, this resonance doesn't last forever. The circuit is losing energy as it's bouncing back and forth. So this wave will eventually lose all its energy and diminish to nothing. Now that we have all that electromagnetic stuff out of the way, let's get on with the real business of building an EMR tablet and pen system. On the left, I'm going to draw a simplified tablet. I'm going to start with a box that just represents the brains of the tablet. And it's going to be connected, of course, to an inductor coil. And then on the right, I'm going to draw the pen, which is its own inductor coil, and the capacitor. Now, on the left is, of course, the tablet. On the right, the pen is just a simple LC circuit, just like I've shown you before. Now, our first change is going to be with the LC circuit. I've drawn it in the inductor for these two parallel to each other. They're aligned, but there's no reason that it must be so. And so we're going to redraw the pen a little bit. And now I will draw it a little differently. I can make it so it's perpendicular. So it's the same design, it's still an LC circuit. Now let's start by thinking about what the tablet needs to be doing. So the tablet is going to have to switch back and forth between two modes. And it's not something that can easily convey in a drawing, but here's what's going to happen. For a very brief period of time, the tablet is going to run a current through the wire, and that inductor is going to form a magnetic field, a changing magnetic field, which will then induce a current in this thing, in the pen. And it's going to do that for a brief moment. And then once it does that and stops, the pen is going to resonate back and forth just like we saw before. So now when the brain is listening, as the magnetic field starts developing around the pen's inductor, it's going to create what, of course, a charge that moves here in the tablet. And so this charge is going to be detected by the brains of the tablet. So back and forth, many times a second, the tablet is sending some current to power the pen and then listening for the resonance of the pen. Okay, and that's why the LC circuit is so important here. So at this point, we have the beginnings of a real EMR tablet pen system, but it's not very useful because all that happens now is the tablet powers the pen briefly, and then essentially the tablet can detect that the pen is close to the tablet, and that's it. So not a useful tablet right now. Let's clear up the drawing and move on to the next step. We're going to draw the tablet slightly differently now. So let's get the eraser out and just erase that wire. Now what we're going to do is we're going to draw this just a little differently. Nothing will really change about the brains. And we'll have the wires coming out of the brains. And instead we're going to draw this kind of board. And what's going to happen here is we're going to take that same inductor and we're going to let it come out of the board and loop around and go right back into the board. So nothing has really changed with the tablet at all. It's just that the inductor is placed on this board. Now our next change. We're going to redraw this inductor. Now I mentioned earlier, I don't need to have so many coils. In fact, I can have just one. So what I'm going to do is I'm going to draw this loop a little differently. I'm going to have it go over and have one coil and come back underneath, and then it's going to go back in. So it's not as if this wire is touching itself, but it's just flat against the board and there's a single coil. And in fact, now I'm going to add multiple coils that have the same kind of layout. Now remember, each one is coming out and coming back into the board. I'll just draw a few more. Now what's happening here is that each one of these coils can deliver power to the nearby pen. Each one of them can listen to the pen. Let's suppose the pen is close. The fact that these coils are arranged along the x-axis, but they're going up and down, means now we can detect the vertical position of the pen. Because if it's at the bottom, then this coil will register strongly that the pen is near. What if the pen is toward the middle? Then of course one of these will register super strongly that signal, and one of these will be a little less on either side. So there are not so many coils on this board. There's not thousands, there's just a small number. There are more than this. But by looking how each one reads the pen, the tablet can triangulate, so to speak, the position of the pen, at least in this case, vertically. Now let's clean that up. Now we're going to go on to part 2 of this determination of position. We have the position of the pen vertically. What about horizontally? Well, we just applied the same principle. Let me create some space here. We'll draw some more wires. We'll draw another board. Except this time, the coils are going up and down. And I'm not going to draw as many coils. And I'm going to be a little loose with how I draw these. Okay, so I only just drew 3 coils. But it all works now. And the pen over here. So now the board here, with the ones that are running horizontally, this one can detect, let's say the pen is at this vertical position, and then this board will detect that the pen is at this horizontal position. That means we have a Y position, we have an X position, so we are able to determine obviously the XY position of the pen, and that's fantastic. So now the tablet is actually a little useful. So what about tilt? Before we get into that, we're going to have to simplify this drawing so it's easier to understand the tilt. So I'm going to erase how these boards are drawn here, and I'm going to draw them as if they're one board. Let's erase these little things. Okay. Now what I'm going to do is I'm going to just draw the coils as simple lines, and I'm not going to be super precise. But each line there is a coil that goes horizontally, and each line here is a coil that goes vertically. So obviously this is a grid. Now it's not literally a grid physically. There's not a grid of wires that touch in this way. This wouldn't work correctly if the wires literally touched in the shape. This is just a visual aid so you understand the next part. Okay, so now to understand the tilt, we're going to erase this pen first, and we're going to draw that same grid, but we're going to draw it as if we're looking right down on top of it. In other words, the grid is going to look like this for us. Now I want you to imagine what happens if we have a pen that's directly perpendicular to this. So it's going to be pointing in the middle. And all we're going to see is sort of the top part of the pen. It just looks like this dot. Now the magnetic field extends through space, and it's going to intersect this grid, and that intersection has a certain shape. If the pen is vertical, the intersection will look something like this. So it's really strong around the pen when it's close to it, but of course it gets weaker and weaker as it goes out. In other words, this shape is very symmetric. We can infer that the pen is not tilted at all, since the shape is completely symmetric. So let's erase all that magnetic field stuff, and then let's imagine where the pen is, if it's tilted. Now it won't be a dot like that. Let's say it's at an angle, and I'll draw it like this. And I'll fill it in so it's obvious that it is the pen. What will the magnetic field look like now? Because it's intersecting a little differently. And so it'll look something more like this. And I'm just going to draw the overall shape first so it's more obvious. So you can see it's no longer just the circle. It's kind of smaller toward one side and much bigger toward the other side. And so this, if you look at how it's going to affect the coils, this is how the tablet can detect if the pen is tilted, because the shape of the magnetic field as it intersects these coils will look a little different. So at this point, we have figured out how tilt must work. And so far, the pen is still simply an LC circuit. Now I've redrawn the pen circuit, and I want to emphasize that the LC circuit is the simplest kind of EMR pen you can have. This may seem like I am exaggerating, but look in the description of this video. There's a link to a YouTube channel called Scanline, and the link will point to an exact section of a video that YouTuber has created. And what you're going to see is that she takes a tuned LC circuit, just an inductor and a capacitor, and she moves it over a Wacom tablet, and you can see what I'm saying is true. Just that circuit, the LC circuit, when it's correctly tuned, will act like a pen, and it can detect the position, it can detect the tilt, and it can be powered by the tablet itself. So how does a pen support pressure? And in fact, I'll have to tweak this circuit just a little bit. So let me redraw this first. And what I'm going to do is draw this very big. Now that I've redrawn this to be so large, let's pick a different color. Let's try blue so it's more obvious what's going on. Okay, you know these pens have a nib, and the nib is just plastic. And I'll draw it filled in a bit. Okay, so that's a plastic nib. What the plastic nib does is it pushes against a ferrite rod. Ferrite rod is inside. But it's a rod, and when you press down the pen, the nib moves, and then it presses against this, which it in turn moves. And there's something pushing back on the other side. We'll imagine it like this. There's a piece of plastic. This is just simple plastic. And around it, sort of pushing it, is a spring. Now I know this looks like an inductor, but it's just a spring that's sort of there pushing up against something. So this is there to offer some resistance so that the pen is pushing back against the nib. So remember what I said earlier, that if you put something in the middle of the coil, it'll affect the inductance, and that inductance change will affect the resonant frequency. So what an EMR pen can do is, as this ferrite rod moves in and out of the coil, it'll change the resonant frequency. And so, for example, the frequency may get higher or lower, and then the tablet can detect that change in resonant frequency as a change in pressure. Well, what about the buttons now that are on the pen? Because these EMR pens usually have at least one button. Well, let's return to what we know. We know that there's a signal being generated at this resonant frequency, and that this magnetic field is developing and growing and changing direction in this kind of sinusoidal pattern. We have a couple of options that are well known to deal with communicating information in this pattern. As you know, we could, of course, increase the frequency or lower it, and the change in this frequency could be used to communicate information, like a button press. Or we could, I suppose, create a larger amplitude and keep the frequency the same and shrink the amplitude. That could also be used to communicate information. Or, and this is a little harder to draw for me because it's a little more delicate, we could change the phase. So instead of when it goes up, it can kind of skip to the next part a little faster than expected, and that could be used to communicate information about the buttons. So these are three options that you could pick to communicate information, and other options are available, but these are some likely ones. And there you have it. So we've shown you how an EMR can receive power. We've shown you how the tablet can sense the pen just because it's close. It's in proximity. It can deliver that power and get information back. We've shown you how position can be determined. That's the XY coordinates. We've shown you how tilt can be detected by detecting how the magnetic field intersects the grid of coils. And then we've talked about how the ferrite rod can be used to change the resonant frequency, and that can be used to calculate pressure. And we've given us some options for communicating other information about the pen, like the buttons. To make this video, I had to rely on so much information from others. And in the video description, I've listed every piece of information I've used to help me assemble this video. Please check them out if you want to learn more about how EMR pens work, or are just more curious about the electronics behind all this. And so this brings us to the end of our journey. I hope this video has given you a new appreciation for how this amazing technology enables you to use a pen in creative applications. Thank you for your time, and I hope you enjoyed this video.